Testing. Okay, Assalamualaikum. Everybody boleh, can you hear me?
Yes. Boleh. Yes.
Okay, so ada lagi 2 orang.
Ada boleh masuk.
Okay, can you see the slide in front?
Yes.
Yeah.
Boleh nampak Okay. Okay, while waiting, okay, I'm going to write something on the board, so just copy it. Boleh nampak tak? Is it too high up? Boleh nampak?
Boleh.
That's nice.
Okay, everybody in? 9, okay. All right. That's just okay. Assalamualaikum. Very good morning to all. Okay. So for today is that you're going to learn about the mathematical modeling of a dynamic system. Okay, for electrical and electromechanical system. Right. So yesterday, a bit recap is that you did the electrical, the modeling for mass, spring, and damper system. And you're given the value for mass, damper, and spring, you get the response of the xt example. So by having the initial condition x double dot, x dot, and x at 0 position, so what is the response time? Okay, so so that is what you have learned yesterday. So for today is that you're going to learn on the electrical and electromechanical system. Right, this one you have actually learned it during undergraduate also on electrical system. Okay, so this one will be very fast, and I'm sure that we are going to finish it early, maybe about 2 hours, and then since you're a master student, so more time is actually spent on the assignment. Okay, assignment using MATLAB, so on. So let's start. Everybody here, Zamzame, Shadik, Danny, Hanif, Kugen, Arif, Ain, Heba. Heba, you there?
Yes, I'm here.
Okay, all right. Okay. So everybody's here. Okay, so let's start. Okay, directly to the contents for this for today. So you have the what is electrical element. So you have RLC, circuit example for series and parallel, and then when you have a complicated electrical system, so what are the transfunction and how you can actually transfer it into impedance. Okay, and then we go to electrical motor. So here is that we are going to combine the electrical part and the mechanical part. Okay, so electrical part, which is the electrical element today, you're going to combine it with yesterday class, which is the mechanical part, right? So next we go to analysis of motor performance, and lastly is the MATLAB and Simulink application. Right? So first of all is the electrical element. So this one is you always already know this circuit. So you have a light bulb. Example, you have a light bulb. So you have the voltage, input voltage. So if we draw this as the normal, the electric circuit is that you actually replace this bulb with R. So you have the R element, electrical element using resistor. So the mechanical description of between number of electron, which is Q, and current is given by this, I equal to dq over dt. Okay, what is relevant because later on you are going to use this dq over dt in the modeling of the time domain. Okay, and so from here is that you get qt is equal to the derivation I of dt. So you have Ohm law, V equal to IR. Okay, so means that the source is actually the element that provide energy. Okay, and the load is the one that dissipate energy. So dissipate, if you have the bulb just now, so you are going to dissipate the energy out. So passive element is example is resistor, capacitor, and inductor, which is not a source, but an active element is energy source that drive the system. So active element is the voltage or current source. Okay? Passive element is the resistor, capacitor, and inductance. So from here is that you can calculate what is the work of the power P, okay, which is work done per unit time. So definition is that the power generated by active element or the power dissipated can be stored by passive element. Okay, so you will get this equation: P power equal to IV. Okay, current times voltage, or you can rewrite it at this one. This one is very simple. So we go to what are the electrical quantities. So you have the symbol here, quantities. Okay, just read this. You have the quantities, you have the unit, and you have the circuit symbol. Very fast. And next is on the electrical network transfer function. Okay, so similar to what you have learned yesterday on the mechanical transfer function. Okay, so you have, instead of mass, you have the capacitance, resistors, inductors. So you can rewrite the equation in time domain as Vt equal to I over C. Okay, I tau d tau, and you can write it in terms of voltage charge. So you have Vt equal to I over C Qt. So in terms of charge. So therefore Vt is equal to this and Vt is equal to this for the inductance. Okay. And if we have the impedance element, why this is important later on is that when you're doing the modeling for transfer function, we are going to use the impedance Z instead of the normal voltage charge or based on the current voltage. So we are going to use the impedance Z. So means that if we see there are a capacitance, then you are going to use 1 over Cs. Okay? And if there are resistor, then you're going to use R. And if there is an inductor, then it's Ls. Okay? So just a bit of recap on modeling circuits. So you know that there are two laws, Kirchhoff voltage law, which is the Kirchhoff voltage law. KVF is the algebraic sum of voltage around any closed loop in electrical system. And Kirchhoff current law is about the algebraic sum of current into any junction is equal to 0. Okay? So we go directly to an example of series resistance here. Okay, you have the voltage source, you have R1, R2, right? And then you have current. So this is simple. Using Kirchhoff voltage law, Vs equal to V1 minus V2 plus V2. So you can rewrite it as this. This one you can actually write it as Vs equal to V1 plus V2 lah. So that's why you get this one. So equivalent to Vs minus what is V1? V1 is IR R1 minus IR R2. So you get 0. So therefore you get this value. So if you see here, the series resistance is that you can actually get the R equivalent. So R equivalent is R1 plus R2 here. Okay. So the voltage divider rule is that, assuming that you are asked to actually calculate what is V1, okay, V1 here over the value for Vs. So V1 is equal to R1 over I. So how to calculate the voltage divider is that if you are going to calculate V1 is that R1 over R1 plus V2. Okay, so you get the first equation, and V2 is R2 over R1 plus R2. So this is called the voltage divider rule. Yeah. So therefore, if you look here, you can actually make a conclusion that V1 over V2 is equivalent to the resistance R over R2. Okay. So next we go to parallel resistance. This is similar to yesterday class. Class for mechanical is that we look at different example when you have a spring in series and spring in parallel. So similar to that. So we have the parallel resistance. So you have the voltage source, you have R1, R2 in parallel. So how you get by this is that you get the value for I1 and I2. So I1 is Vs over R1, I2 Vs over R2. Then using the Kirchhoff current law is I going in equal to I1 plus I2. Okay. So therefore, substitute I from these two, you will get Vs over Vr, Vs over Rr, R1 plus Vs over R2, right? So therefore, if you look at this, is that you can actually get R equivalent equal to 1 over R equal to R1 over R1 plus R2. Okay. Current divider rule is actually the opposite of voltage divider rule. So if you want to calculate what is I1, so I1 here is equivalent to R2 over R1 plus R2 times I. Okay. So in contrast, I2 here is R1 plus, R1 over R1 plus R2 times I. Okay. Am I going too fast? Everybody? Does that semua okay? Or it's too boring? Okay.
Okay.
Okay, all right. So next we go to power and power and energy. So before this, in the previous slide, we were talking about how to get for power. So we have the equation for power equivalent to IV. Okay. So if you want to calculate what is the energy stored in capacitor, okay, so you can use this equation, general equation, then you will get the final equation E. The energy stored is 1 over 2 CV squared, and for inductance is that 1 over 2 Li squared. Okay, so therefore, if you were to actually write all of the resistance value here, so resistance V equal to IR, then power, you can write it as V squared over R. For capacitance, notice that for capacitance inductance, it's not power, it's energy, because it's energy stored. Okay, so it's given by E 1 over 2 C V squared, and for inductance is E equal to 1 over 2 Li squared. Right? Any questions so far?
No.
Nampak hidung you. Oh, tak boleh ni, tak best. Okay, any question? No, nothing. Okay, tadi macam nampak hidung. Okay, nanti saya tegakkan balik lah when we go for the Cramer's rule. Alright, so next we go to the circuit example and transfer function and impedance. Oh, this meeting will end in 10 minutes. Alright, not yet. Okay. So we go to the first example, current and power in resistance circuit. So this is simple example of one loop. So for the circuit shown in figure 6.21. So if you see here, all of the example is given a figure 6.21. It's actually referring to the pump book, pump dynamic mechanism book. So if you're borrowing the book, then you can refer to the book. It has more detailed explanation. Okay, for the circuit in this figure, the applied voltage is given 6 volt and resistance is R. So determine current and power that can be produced by power supply. Okay, this one is very simple. So I equal to Vs over R, then you can get what is I. Then power is I dot Vs, so you get 3.6 watt. So I is 10 times Vs is 6. Okay. Then we go to the second example, a summing circuit. Okay. So you have two voltage supply, V1, V2. Then you have R2, R1, and R3 here. Okay. So the question is, derive the expression for V3 as a function of V1 over V3. Okay. So means that they ask you to get what is this with the function of V1 over V2. Okay, and they give you the value for R. Okay, so first what you need to do is that you get using the voltage current relationship, get what is the value for each resistor. So first get what is the value across this. Okay, so V1 equal to IR I1 over R1, right? Okay, and then rearrange it, you get this one. So I1 equivalent to V1 over R1. And what is V1? V1 here is actually V3, V1, V1, the voltage across here is that actually V3 of minus V1, V3 minus V1. So that's why you get the first equation here. Okay, second is that get what is I2. I2 is V2 minus V3, V2 minus V3 here, then you get what is over R2. And I3 is V3 minus over R3. Okay. So, and you know that conservation of energy or charge at a point here is actually I3 equivalent to I1 plus I2. So you have I2 here going in, I1 going in, then you have I3 going out. So therefore you get I3 equal to I1 plus I2. So substitute all of this value to here. Okay. So if I3 you have V3 over 3 and so on, substitute it here, then in the end you can get the equation V3 equal to 0.4 V1 plus V2. So this is by actually substituting the value for R1, R2 is equal to 10 and R3 equal to 20. Okay, simple Simple kacang Okay, very easy. Okay, next. Okay, we go to the application of voltage divider rules. So the question is, obtain the voltage V0 as a function of applied voltage Vs. So right now, they ask you to get what is V0 with the function of Vs. So what you need to do is that you need to simplify first the circuit. Okay, how to simplify is by actually working it from right to left until it's simplified into one loop only. So right now you have two loops. Okay, so first one is that, okay, using the voltage divider rule, get what is the value for V0 first, since the question is that obtain the voltage V0. Okay, so V0 is, using voltage divider rule, is R4 over R4 plus R3, okay, over Vs. Since you know Vs here is equal to this, so you have, VA here. So this is VA, okay. So V0 is equal to R4 over R4 plus RT over VA. So that's why you can get this first equation. Substitute R4 value and R3 value, you get V0 equal to 1 over 4 VA. Okay, for first question, first equation. The second equation is that, okay, try to simplify this series circuit, make it into equivalent circuit. So you have learned in the previous slide on, if you have series, then you just add it up. So this one, if you add it up, it become 8. Okay, 6 plus 2 is 8. So you get this simplified circuit. Then from here, you see that it become a parallel circuit. Okay, parallel resistor. So you have 10 and 8. So get what is the equivalent here. So assuming that we are giving it as RP here, so 1 over RP is equivalent to 1 over 10 plus 1 over 8. So you get 9 over 40. So this one, just refer back to the parallel circuit. Just remember that you have two parallel here. Okay, this is the equivalent. Okay, so 1 over R is 1 over R1 plus R2. So that's what it means. Simplify it, you get this. So make it, draw back the circuit into one loop circuit. So you have 5 and then you have 9. This one is 1 over RP, kan? So it become 40 over 9. Okay, for the resistance. Now it become much more simple to actually calculate. So get what is the value for VA using the voltage divider rule. So VA equal to 40 over 9 over 5 plus 40 over 9 times Vs. So you get 18 over 70 Vs. Okay, now go back to the first equation just now. Okay, so first equation given by this, V not equal to 1 over 4A. Did you get the A value just now? Yes, right? This one was the value for VA. So VA, substitute that, 18 over 17 VS, then you get the final equation here, which is you get V naught as a function of VS. So you get 2 over 70 VS. Okay? And everybody can follow? Eva?
Yeah.
Follow it?
Yes.
Right.
Yeah, okay.
Next, we go single loop. Okay, now compared to this one is just a simple equation. Normally, you learn it in circuit theory. Okay, circuit theory. Right now, we are talking about dynamic. Okay, dynamic mathematical modeling in dynamic systems. So we are using it in terms of time domain. So we are going to try to use the concept of like what you have learned yesterday in mechanical system. So first is that in this exercise is that you need to refer to this table in slide number 7. Okay, refer to this. So what you're going to refer is actually this part and this part. Okay. Okay, so here is that find the transfer function relating capacitance Vs. Okay, relating Vs with input, Vc with Vs. Okay, so you have L, R, and C value. Okay, let's do the equation. Okay, using this in terms of current source. So it means that we are going to use this one, voltage current source. So it means that Vt equal to 1 over C ID tau. Okay. So let's look at the equation. So we have Ls in terms of time domain. You write it out as L di over dt plus RIT plus 1 over C. Okay, I tau d tau. So you get Vt, first equation. And then you know that the current is actually the derivation of the charge. Okay, so you have dq over dt, substitute that, then you get this equation. Okay, and then you know that q is equal to c vc, then you get the second equation. So taking the Laplace transform here, okay, lc d to the power of